Now that we know how to evaluate exponential functions at certain values of x, we can look towards their graphs. So here we have an exponential function, f of x equals 2 to the x. This is an exponential function with base 2. So to figure out what it graphs like, let's just pick some points. So let's evaluate this function at f of negative 2, f at negative 1, f at 0, f at 1, and f at 2. So here we have some properties that we can just go ahead and use to evaluate this and get a better value to work with. So we have base 2, and then the variable is in the exponent, so I evaluate it at negative 2, which the negative exponent gives me 1 over 2 squared, which is going to just be 1/4. So at negative 2, I go left 2 from the origin, and I go up just a little bit to give me my first point. Let's continue to work with the other values. So 2 to the negative 1 is just going to give me 1 over 2, and there's nothing more to do there. So again, negative 1, 1/2 is now plotted on the coordinate plane. Plugging in 0, we get 2 to the 0, and as we mentioned before, it is just 1. So right here we have our y-intercept. Now I said this is very important. And we'll discuss why on the next page. So then we have 2 to the 1, which is just 2. So we evaluate that and put that in a point in the first quadrant. And the last one is really just to get us more of a curve. It would be 2 squared, which is 4. So again, in the first quadrant, and I connect these in a smooth curve. And you can see why we call these exponential functions. They essentially rise very, very quickly. It's important to note that as we go to the left, or as x goes to negative infinity, the graph will never go below the x-axis. The reason being is we can't pick any value for x that will allow us to get a negative number here. Now let's look at what happens when we have a base that is a fraction. So the main points that we're really going to need to work with are just the points right around the origin. And then we can really use transformations just like we have before to go ahead and work with the rest of the graphs. So I'm going to just do g of negative 1, g of 0, and then g of 1. So that is going to give me 1/2 to the negative 1. Properties of exponents say, you know what, the exponent affects the numerator and the denominator separately, which means the 1 is going to go to the denominator, the 2 is going to come up to the numerator, so we have just the value of 2 when x is negative 1. So here we have this point in the second quadrant. And again, you maybe can start to see why this 0 is so nice, because again, regardless of the base, anything to the 0 power will be 1. So again, we have our y-intercept. And then 1/2 to the 1 power is just 1/2. So that puts us here. And now that we have a general idea of what the shape of the curve looks like, you may just want one more point to go ahead and try and get a smooth curve. We have an exponential function. This time is decreasing on negative infinity to infinity. Of course, you may have been able to just do it this way as well. You could take the 2 and put it in the numerator, and then you'd have 2 to the negative 1 to the x. And then whenever you raise a power to another power, you simply multiply the exponents. So this gives me 2 to the negative x. And based off of what we know about transformations, this negative in the exponent is going to be a reflection. The question then is, over what axis? Well, because it's in the exponent, then the x's in the exponent is going to be causing a reflection over the y-axis by taking all of the positive values and making them negative, and all the negative values making them positive. So you can see we have a reflection over the y-axis. If you compare these two graphs, well, we already figured it out. we have our first encounter with our transformation. So if we go down the bottom of the page, the relationship that we see between the graphs of f and g, it is simply a reflection. Of course, all of the other transformations, such as shifts, stretch, shrinks, will also apply.